Hello. Okay. Sorry, the mic was off. Okay. So I'm Supriya Adhikari, and this is the week 9 of the Discrete Mathematics course. Uh, week 9 of the live session for this Discrete Mathematics course. And first, I will discuss the week 8 problems. So this is the first problem from week 8. So in this problem, what we have here is that we have 4 statements, and we have to check the correctness of each of the statements. So the first statement is given as in an undirected graph, there is always a even number of vertices with an even degree. So when we are talking about graph in this section, all the graphs that we will consider are simple graphs. So if we consider a simple graph like this, with 5 vertices, then as we can see that V1 has degree 4, and the vertices, they have degree 1. So V1 is the only vertex with even degree. And as the statement 1 says, that in an undirected graph, there is always even number of vertices with even degree. And as you can see, that this is not true, because in this particular example of this graph, we have the only one vertex with even degree. So statement 1 is not true. What about statement 2? Statement 2 says that a tree has no cut edge. Now, this is also not true. Why? Because we can prove that every edge in a tree is a cut edge, or we can also call it as breach. And why is that? So, so what is the definition of a tree? So the definition says that a tree is a graph with no cycle. So there may not exist any cycle in a tree. Now consider that there exists one edge in a tree such that, so consider a graph like this. Okay. So this is our graph G. So there might be some edges and some nodes over here, and consider this to be one of the edges between two vertices. Let's call it as U and V. And if this is the edge, and consider, if possible, let E be not a cut edge. And if that is true, then if we delete this E, then still this graph, the rest of the graph will be connected. So if we delete this E, then still this graph is supposed to be connected. So that means that there must exist a path from U to V in this graph that does not involve this edge E over here. Now, if we include this edge E again, then this path over here, along with this edge E over here, this will create a cycle. But that is a contradiction, because a tree does not have a cycle, and therefore every edge is basically a cut edge in a tree. So the second statement is also not true. Now the third statement is that in an undirected graph, there are always an even number of vertices with an odd degree. So let us consider a graph, any graph G, and this graph is basically have a vertices and edge set. Now we know that the degree, sorry, we definitely know that 2 multiplied by the cardinality of E is equals to the sum of all degrees where V belongs to this vertex set. This is known. Now consider that we Consider this vertex set to be a union of two sets, VE and VO. So VE is basically all those vertices such that the degree of V is even. And similarly, VO is basically the set of all vertices such that the degree of V is odd. So this VE and VO are basically disjoint sets. So we can write it like this. This is nothing but equals to all the vertices in VO multiplied by the degree of V plus the summation all the vertices in degree of VE. Sorry, all the vertices in VE. Okay. Now consider this term over here. So this is twice of the cardinality of. So this is equals to this. Now this is even number because according to the definition, this degree of V is basically T of V is basically even for each of this V in VE, and therefore this sum will be an even number. This sum is again an even number. So technically, this should also be an even number. Now, if this is an even number, and each of this, and according to the definition of VO over here, so each of this dV this should actually be yeah, each of this dV should be odd. Now, how is it possible that the sum of odd numbers is even? The only possible way to do that is the cardinality of VO is even. It is only possible when this is even. This number of elements in VO is even. So that is this statement is correct. That is, if an undirected graph, if we say the number of vertices that have odd degree, that should be an even number. Okay. So now we have the fourth statement. So in the fourth statement, we have a breach cannot be a part of a simple cycle. Sorry. Okay. And finally, we have a breach that cannot be a part of a simple cycle. So what does that mean? So if we have a cycle, a simple cycle like this. It says that if we have a simple cycle, then none of the edge cannot be a breach. That's what it meant by this statement over here. And this is also true because since this is a cycle, then this is a connected graph. And I mean, we know what is a cycle. So if we even delete, sorry, this edge over here, then still this graph will be connected. And there will always be a path from this point to this point, UV. You take any edge, if you delete that, then still the graph will be connected. So that edge will be a bridge. So none of the edges is a bridge. Or cut it. So this is also true. And so therefore, both 3 and 4, these are correct. So option D in the question, that is correct, and ABC are not correct. Now we have problem 2. So in problem 2, we are given a graph, which is basically the complete graph K6. And in this complete graph, it is given that if A is equals to P of G, the vertex connectivity So this K of G is, sorry, it's not K, it's kappa. So kappa of G is basically the vertex connectivity of the graph G, and this lambda of G is given as the edge connectivity of the graph G. And we have to find the A multiplied by B. So now, what was the definition of vertex connectivity? So the definition of a vertex connectivity was that the the minimum number of vertices that can be uh, deleted to the minimum number of vertices that can be deleted to make the graph disconnected. So this is our kappa of G. That is the vertex connectivity. Similarly, what we have is the lambda of G, which is the edge connectivity. That is, again, similarly, the minimum number of edges. So instead of vertices, we have minimum number of edges. So this is the definition of kappa and lambda G. Okay. Okay. So now for key 6, so key 6 is like this. Okay. So key 6 would look like this. Now for key 6, what is kappa of G? So kappa of G is basically the minimum number of vertices that we can delete so that the graph becomes disconnected. So if we consider deleting only one edge, sorry, only one vertex. So consider this like this. So if we try to this one, then still this will actually be a K5 graph. Then again, if we delete any vertex like this, then this will be a K4. If we delete one more vertex, this will be a K3. So deleting one vertex, so from Kn, if we delete any one vertex, then that will actually give us Kn minus 1. And similarly, if we delete one vertex from the Kn minus 1, that will give us Kn minus 2 and so on. So the graph will still be connected if from a complete graph, if we delete one vertex, then that particular graph will still be connected until and unless we delete all the vertices like this. And then, okay, so until basically we need only vertex left. Okay, and therefore what we can say is that the vertex connectivity of a graph is basically the for this case 6, this will actually be equal to 5, because after the definition of vertex connectivity, this was modified. The minimum number of vertices that can be deleted to make the graph disconnected, or uh, we are left with one vertex. So that was the definition, and similar for this one. So in this case, this was the minimum number of edges that's deleted, so that we are left with so the graph is disconnected, or we are left with a null graph. Okay, so over here we have the vertex connectivity as 5. Again, for the edge connectivity, now for the edge connectivity, okay, so now if we delete one edge, any one of the edge like this, then what we can say about this, so let's say that UV are basically the UV is the edge that we have deleted. Okay, that means the vertex, the edge that connects U and V, the vertex U and V, we have deleted that edge, that particular edge over here. Then U and V are still connected because given any other vertex over here, let's say T, we can say that there exists a path UTV like this. So the only way that we can make a graph disconnected, a complete graph disconnected, is to delete all possible edges corresponding to one particular edge. So you have to delete all these edges. This is the only way so that we can make, I mean, this is the not only way, but uh, this is the way that we can delete minimum number of edges to make this graph disconnected. So the edge connectivity again is lambda of g, which is equals to 5, because the degree of each of the vertices is 5 for physics, and therefore we need to delete at least 5 edges to make this complete, make this graph disconnected. So the edge connectivity is again 5. And what is the minimum degree? Okay, so we have to just find the value of A star B. And A star B over here, since both is 5, so A star B should be 25. Now in the problem number 3, we have to find which of the statements are false. So the first statement is that a graph with bridges cannot have a cycle. A graph with bridge cannot have a cycle. So this is not true. How can we say that? We can just give an example like this. So suppose that there is a graph like this, which is a cycle, and again, we consider this. So definitely this graph has a cycle. If we consider this graph as G, then this is our cycle. But if we consider this one, then this edge is nothing but a bridge. So this is a simple graph with a cycle, but it definitely have a bridge. So this statement is not true. And we have to find all the statements that are false. The second statement is that an undirected graph with degree sequence 4433221 can be formed. So we have to check whether this degree sequence is possible or not. So let's check that. So there are 1, 2, 3, 4, 5, 6, 7, 8. So seven, sorry. So there are total 7 vertices. So to check whether a degree sequence is correct or not, or a degree sequence is graphical or not, uh, the first thing that we should check is this condition. Right. If this is not true, then definitely what we can say is that this is not possible. I mean, to check this, so if all the degree of all the vertices, if the degree of all the vertices are there, then the first thing we can do is that we can just sum it up. Then what is the sum of this degree values? This is 8 plus 6 plus 4 plus 1. So that should be 90. So it says that twice of e should be 90, but that is not possible. Why? Because the number of edges should always be an integer. And that implies that twice of e is always even. And in this degree sequence that is given over here, this degree sequence is not possible for any graph, any undetected graph. So this is also a false statement. What about the third statement over here? So third statement says that a wheel graph having n vertices has twice of n minus 1 edges. So consider a wheel graph. So a wheel graph have a cycle of size n like this. So this is a cycle of size n. So this is like v1, v2, vn minus 1. Okay, so wheel graph must have a cycle of n minus 1 cycle, and at the middle we have vn, the nth node, and then each of these nodes are connected with the central vertex like this. So this is a wheel graph. Now in a wheel graph, the question is that the number of vertices should be twice of n minus 1, and that is true, because since this in this cycle over here, the number of edges should be n minus 1, because the cycle is, this is a cn minus 1, this cycle over here. So the number of edges should be n minus 1, and each of these n minus 1 vertices is connected to the central point. So that is again n minus 1 many edges. So the total number of edges should be twice of n minus 1. And finally, a complete graph is also a real graph. That is definitely true. Why? Because if we consider kn, so in kn, if we consider any vertex v, then that particular vertex has to be connected to each and every one of the rest of the n minus 1 many vertices. So that means the degree of v for a complete graph is n minus 1. And according to the definition of a regular graph, each of the degree should be equal. So a R regular graph was defined as that the degree of v is equals to R for all v in the vertex set. And definitely a complete graph is a regular graph because all the vertices have the degree n minus 1. So this is a regular graph. So the only false statements are A and B. In problem 5, we have to choose the correct statements. So the first statement is given as the maximum number of possible edges in an undirected graph, undirected simple graph with n vertices, and key connected components is n choose 2 minus nk. So this value is nothing but n choose 2. So basically, we will find A and C together. Okay. So if we can, so as you can see, in A and C, the only difference is this term over here. So we just have to justify whether this is true or this. Okay. So technically, first we will claim, our claim is that, so basically in the over here the maximum number of edges in an undirected graph with k connected components. So we just have to find a graph with k many connected components. So this can be like this. So each of these are connected components, and the first component has n1 many vertices, second component n2, n3, and in K, something like this, such that the sum of each in I turns out to be the complete N. Okay? So if we want to find the maximum number of edges, then we have to consider each of these connected components as complete graph. So the total number of edges in this particular graph is nothing but n1 choose 2 plus n2 choose 2, nk choose 2, something like this. Now, the first claim is that if we choose all this ni values as this, n1 is equals to n minus k, and n2, n3, n4 upon k, all of these values we choose as 1. Then for this particular case, we will find the maximum number of edges. So this is our claim. Now, how can we prove this? So suppose that this is not true. So if this is not true, then we can say that, okay, so there are some component which has n1 many vertices, and basically some has n too many vertices, and both n1 and n2 are greater than 1. So over here we have considered that only one component has greater than 1, that is n1 minus k many k minus k many vertices, and rest of the components are basically consist of only one vertex. So the negation of this statement is that there are at least two components which has more than one edges. So without loss of generality, we can consider that n1 is greater than n2. This is greater than 1. Now, the thing is that this is k in 2 and this is k in 1. Now, we consider any vertex over here. So the degree of that vertex, so we consider a vertex v over here. Now, degree of that vertex v is basically n2 minus 1. Now, what we do is that we delete that vertex from here, and we add that vertex over here, and we delete that vertex from here, and we add that vertex v over here and connect to each and every one of the vertices in Kn1. Then the total number of edges would now be whatever the number of edge over that was over here, minus into minus 1, because we are deleting this vertex from here, plus n1 minus 1. Sorry, plus n1. Because we are adding n1 many edges over here. So that will be nothing but cardinality of E plus n1 minus n2 plus 1. And since we know that this n1 is strictly greater than n2, then therefore what we can say is that the number of edges that we are basically the number. Okay, so this can be like this. So that the number of edges in this newly formed graph is definitely greater than the number of edges that was before. But what we have to assume is that these connected components, I mean the way that we have created this connected component, that has the maximum number of edges. So that is a contradiction, and therefore what we can say is that our claim is correct. That is, if we consider only one component like this and rest of the component with only one vertex, then only we have the maximum number of edges. And so the total number of edges should be n minus k choose k choose 2 plus okay, the total number of edges should be n minus k choose 2, and which is nothing but this. Oh, sorry, this is not n minus k choose 2. So over here, these are k minus 1 many vertices that are 1. So this should be n minus k plus 1. So the total of edges should be n minus k plus 1 choose 2. It's the maximum number of edges. And that is this term over here. So C is 2. And the option B is given as if G is a complete bipartite graph with the partition V1, V2, then there exists exactly 2 vertex cut. So what is a vertex cut? So vertex cut is basically a set of vertices. By deleting those set of vertices, we can completely make the graph disconnected. Okay. So consider this over here, like this. So this is one simple graph like this. Now, if we delete any one vertex, then definitely this graph is still connected. I mean, sorry. So basically, if we consider this set of vertices, only two, the set of vertices, only two vertices, a set with two vertices. Then if we delete this set, then what we will have is this. So this is a disconnected graph. So this is one vertex set, sorry, vertex cut. Again, we can consider this set to be one vertex cut. This can also be considered as a vertex cut. So there can be multiple vertex cuts. Okay, so the question is that if we consider a bipartite graph, a complete bipartite graph, with V1 and V2 as the partitioning sets, then it has only exactly exactly two vertex cuts. So if we consider a bipartite graph like this, so we have V1 set over here and V2 set over here, and this is a complete bipartite graph. That means that each of the vertex over here has an edge to the edge to a vertex over here, and vice versa. So now one vertex cut can be this set V1. Why? Because if we delete this vertex, if we delete this set of vertex, then all the edge will be deleted, and we know that in a bipartite graph, this set V1 does not have any edge among among the nodes in V1, and therefore this set V1 will be a disconnected graph, and this set V2 also will be a disconnected graph because V1 is deleted. Okay, so V1, V2, these are vertex cut, and there is no doubt in that. But can there exist any other vertex cuts? So how can so if we delete a proper subset of V1, would that be a vertex cut? So now, if we have already deleted a proper subset, so that means there exists at least one V over here in V1. that is not deleted yet. So now we have to prove that this is still a connected graph. How can we do that? So this V over here, so consider if there existed another U over here in V1. So does there exist any path from U to V? Then definitely there exists a path, because since we are not deleting anything from V2, and this is a complete bipartite, so then there exists a path like this. And this is over here, let's say Z is any point in V2. So we can definitely find a path like this. Similarly, if we consider any 2 points over here, let's say U dash V dash, then there exists a path like this. So that means that this graph is still a connected graph if we only delete a proper subset of V1. And similarly, if we delete a proper subset of V2, then that will still be a connected graph. The only way that we can make this graph completely disconnected is that we delete the complete V1 or the complete V2. Okay. Now, option D, over here we have the sum of each connectivity of each connected component of a disconnected graph G is equal to the each connectivity of G. So this is definitely not true, because if you consider connected component like this, and the graph G is basically nothing but the complete, the graph consisting of all these components. This is the graph G. So graph G is already disconnected. So the already disconnected. So the H connectivity of the graph G, it is already 0. But if we consider these as complete graphs, C1, C2, C3, C4, all of them, if we consider all of them to be complete graphs with vertices, let's say N1, N2, N3, N4, then the each connectivity of each of these components is definitely greater than equals to 0. Sorry, greater than 0. So therefore, this is not true. So in the fifth problem, we have a cycle with n vertices is isomorphic. We have to prove that a cycle with n vertices is isomorphic to its complement. Oh, sorry. It is given that a cycle with n vertices is isomorphic to its complement. So we have to choose the possible values of for n. So now consider a graph with n vertices, a complete graph with, a cycle with n vertices. So this is a cycle with n vertices. It's a CN. And it's saying that the complement of this graph is isomorphic to it itself. Now, degree of each of the vertices in CN is 2. And then if the number of vertices is n, then the degree of each of the vertices, okay, so it's considered that's G. So degree of each of the vertices in the G complement, that should be nothing but n minus 3 minus 2. Why? Because in a cycle, we have it like this. So if this is V, then V is connected to 2 other vertices. Let's say U1 and U2. And there are n minus 3 many vertices that it is not connected to. Okay. So this is n minus 3, because the total number of vertices is n. So and 3 vertices are already here. So there are n minus 3 vertices that it is not connected to. So should not be -2. So therefore, what we can say is that the degree of this vertex V in the complement of this graph, in the complement, these two edges should not be there, but these edges will be there. So that should be in -3. So, and if we are and as we know that in a cycle, all the vertices should have degree 2. And if this is true, that a cycle is so basically if Cn has to be isomorphic to the Cn complement, then degree of each of the vertices in the Cn complement, that should also be 2. That is, n -3 should actually be 2. This implies that n is equals to 5. So n is equals to 5 is the only possible way such that the Cn is isomorphic to Cn bar. But the question is that is it true that Cn will be C5 is isomorphic to C5 bar? What is a C5? So C5 should be like this. So this is our C5. And what about the C5 complement? C5 complement is now name this as V1, V2, V3, V4, and V5. Then we can map it like this. So V1, V2, V3, V4, V5. So this is basically the way that we are mapping this two vertices, two graphs. So this is our C5 complement. Then this is actually isomorphic. This graph is isomorphic to C5 bar. So for n is equals to 5, it is possible. Okay, so now okay, so in this problem, we have given three non-negative integers L, M, and N, where it follows this condition: L is less equals to M and less equals to N. So we have to construct a simple graph with vertex connectivity L, edge connectivity M, and minimum degree being N. So how do we construct this graph? So basically, we will take key n plus 1 graphs. So two key n plus 1 graphs. So if we consider this key n plus 1 graphs, then we can assure that each of the vertices in this graphs, they all have degree greater than, sorry, degree n plus n. But this graph is disconnected, so we need to somehow create a connected graph. So to do that, what we will do is that we will take m many vertices over here and l many vertices over here. Now, okay, so the number of vertices, so this L is basically less than M. So now what we do is that we just first we connect it like this. Okay, so we take L many over here and M many over here. And we can take the other way around, but still. Okay, so now what we'll do is that we just connect this L many vertices with this M many vertices. So the first L many vertices is connected to the first L many vertices in this choice of vertices, and this rest of the vertices we can just connect it in any manner we want. But each of the vertices in this M set should be connected to at least one of the vertices in this L set, and vice versa. Each of these each of the vertices in this L set should be connected to at least one of the vertices in this M set, so that we will actually have L many edges. So these edges, the number of these edges, this will be L many. Okay? Sorry, these are not L many, these are M many edges. Yeah, there should be M many edges. So what is the vertex connectivity? Now, if we since this is kn plus one, then each of the each of this component, this kn plus one component and this kn plus components, the vertex connectivity over there are in and n respectively. So if we delete n many vertices in that particular component over there, then this graph will still be connected. But if we delete these n many vertices over here, then this will delete these edges as well, and that will create two connected components. And again, if we delete this m many vertices over here, then this will also create the two connected components. Sorry, two connected components, and therefore we can say, and since L is less than equals to m, then we can say that the vertex connectivity is L, because the definition of vertex connectivity is the minimum number of vertices that we need to delete to make that graph disconnected. And for each connectivity, as we can see that if we delete all these m many edges, then this will make two connected components with n plus one many vertices each, and therefore the edge connectivity is again m. So this is how we can construct this graph. In problem 7, we're given a simple graph G with 6 many vertices, V1 up to V6, and it is given that G minus V1 and G minus V2, they both have 7 edges. G minus V3 and G minus V4, they have only 6 edges in the graph. And G minus V5 and G minus V6, they have only 5 edges. So we have to find the total number of edges in the graph. Now, what happens if we delete one vertex in a graph? So if we delete a vertex in a graph, then all possible edges in that particular graph are also deleted. So if the total number of edge is V in G, then in G minus V, the total number of edge would be the number of edge minus the degree of V. Because all these edges that were incident with this vertex V, they are all deleted. So the total number of edges that we're deleting from this particular graph is degree of V. So now it is given that G minus V1 and G minus V2 both have 7 edges. So this gives us that the E minus degree of V1 is equals to the cardinality of V minus the degree of V2. They are both 7. Similarly, if it is given that G minus V3, G minus V4, they both have 6 edges. Then that implies that cardinality of V minus degree of V3 is equals to cardinality of V minus degree of V4. Second, 6. And finally, if G minus V5 and G minus V6, they both have 5 edges, then this is true. And if we add them all together, then that will give us 6 of 6 multiplied by the cardinality of E minus the sum of all degrees I is equals to 1 to 6. This should go to twice of 7 plus twice 6 plus twice 5. So this will give us and what is the sum of all the degrees of each of the vertices? So that should be twice of. So this will give us 18. Twice of 18. And this finally gives us that the cardinality of is nothing but 9. So over here we have to draw a simple connected non-complete graph. Simple non-complete graph G, where the each connectivity, vertex connectivity, and the minimum degree, they are all same. Now, if you can consider a complete graph, this is true because the edge connectivity, the vertex connectivity, edge connectivity, and minimum degree, these are all nothing but 3 for K4. But we have to find a non-complete graph that actually have this property. So consider this graph. So in this graph, first of all, what is the vertex connectivity? So if we try to delete any one vertex in this graph, then this graph will still be a connected graph. So if we try to delete this graph as, this vertex over here, and this is still a connected graph. Similarly, if we try to delete this graph, sorry, this vertex over here, then this is still a connected graph. And similar for these vertices. But if we do delete the vertices, this and this, then this gives this creates this graph disconnected, and therefore we can say that the vertex connectivity is 2. That is, we need to delete minimum at least 2 vertices from this graph to make this disconnected. And what about the edge connectivity? If we try to delete only one edge from this graph, like this, or this edge, then definitely these are connected. This is still connected. But if we try to delete this edge, then still this is a connected graph. So therefore, deleting one edge will not make it disconnected. So maybe we should try two edges. And if delete these two edges, then this will make this whole graph disconnected. And therefore, the edge connectivity is again 2. And the minimum degree, as we can see that over here, the degree is 2. So the minimum degree is 2. So this is one example where the minimum degree edge connectivity and vertex connectivity are all same. And this is a non-complete graph. Okay. In problem 9, we have a graph G, which is V1, U1, and G2 as V2, V2. Now, we have the cardinality of Vi and Ei given as Ni, Mi, respectively. And we are given the Cartesian product of these two graphs, G1 and G1 cross G2, defined as this. Okay, so this is not a Cartesian product, this is the product of two graphs. And this is defined as this. So each of the vertex, we consider the vertex sets of this new graph as V1 cross V2. That is the Cartesian product of this two sets, V1 and V2. And we create and we say that two vertices UV and U dash V dash are adjacent to the graph G if and only if U is equals to U dash and V is adjacent, or we have that V is equals to V dash and U is adjacent to U dash. So consider things like this. So if in the graph G1 we have U like this, and in graph G2 we have an edge like this. If this is U and this is V1, V2, then we say that U V1 and U V2, between these two vertices there is an edge in the graph G. So this is the graph G1, this is our graph G2, and in the graph G, which is G1 cross G2, we will have an edge between this UV1 and UV2. So first we have to give, for this example, we have to draw this, draw the graph G1 cross G2. So G1 is given as this. G1 is given with two vertices, U1 and U2. And there is only one edge in G1. Also, the G2 vertex, sorry, the G2 graph is given as U1, U2, U3. Sorry, U1, U2, U3. And V1 and V2 is connected, V2, V3 is connected. So V1, V2 and V2, V3, these are connected. So now we have to find the G1 cross G2 graph. So for G1 cross G2, we will actually have 6 vertices. So first vertex will be U1, V1, U1, V2, U1, V3. And over here we will have U2, V1, U2, V2, and U2, V3. So the condition is that if u1 and u2, the first component is equal, then in the second component, if the vertices in the second component they have an edge, then there will be an edge in this graph. So over here, u1 is v1 and v2, they have an edge over here. So we can say that there is an edge from u1 v1 to u1 v2. Similarly, there is a from u1 v2 to u1 v3. But from again, these two components over here, they have the second component equal. Then at least first component must have an edge between them. So definitely they have an edge u1 and u2. There is also an edge over here and edge over here. And over here, since the first component is same, then similarly we will have edge like this. So this is our G1 cross G2. Now we have to derive the number of edges in G1 cross G2. So first, okay. So what is the number of edges that that is in G1 cross G2? So consider one vertex over here in G1, and in G2 we consider one edge. Okay, so V1, V2 are basically the endpoints of this edge, and over here we have U1 in G1. Now corresponding to this setup, we will have an edge from U1 V1 to U1 V2. So corresponding to one particular, corresponding to one vertex in G1 and one edge in G2, we will have. So this will contribute. So this will basically construct one edge from U1 V1 to U1 V2. And similarly, consider one edge V1 U2 in G1 and V1 in G2, then that will generate a edge U1 V1 to U2 V1. And this will be completely different from this one. So how many edges will be constructed using this setup? I mean, this kind of constructions. That is one vertex from G1 and one is from G2. So that should be the number of vertex in G1 multiplied by the number of edges in G2. And similarly, given one edge in G1 and given one vertex in G2, we can construct a total of, given if we can construct one edge, and using this logic, we can construct a total number of, this should be M2, M1 M2, and over here we can construct M2 M1, this many, this many edges. So the total number of edges in the graph G, that is nothing but N1 N2 plus N2 N1. So this is the total number of edges in G1 cross G2. Now the third question is to derive the number of derive the degree of the vertex, U, V, and G. So what is the degree of the vertex? So if we consider So if we consider a vertex in G, so G is equals to G1 cross G2, and we consider UV as one of the vertex. Okay, if we consider UV as one of the vertex, then how many ways that we can consider edges uh, from this vertex UV? So one way is that we consider U in G1 and we consider any edge in G2 with V as one of the endpoints and some V dash over here. Then there will be an edge from UV to UV dash. And the total number of ways that we can consider such edges is uh, degree of V. Because it only, the number of edges that is adjacent to V. So corresponding to each of the edges that is adjacent to V, we can consider an edge in G, G1 cross G2. So the total number of edges that we can consider in this manner is degree of V. And similarly, not similarly, uh, and another way to consider is that we consider V vertex in the graph G2, and we consider an edge over here that is adjacent to U. In the similar way, the total number of this will give us an edge from UV2 dash V, and the number of such edges that is considered in G1 cross G2 is basically nothing but degree of U, because corresponding to uh, each of the edges that is adjacent to U, we are basically finding this edge. So the total number of edge that is uh, adjacent to this vertex UV is nothing but degree of V plus degree of U. Sorry, the degree of UV. This should be degree of V plus degree of U. So now let's move on to the problem 10. So in problem 10, we are given a combinatorial. We have to give a combinatorial proof for this identity. Now, what is in choose to? So in choose to is if we consider a Kn or a complete graph with n vertices, then the number of edges in that Kn is in choose to. We know that. So we have to prove that in choose to is nothing but this. So how do we do that? So we first divide this n many vertices into two parts. We consider k many vertices over here and n minus k many vertices over here. And we have to we basically have to create all possible edges from each of the sorry each of the vertex should be connected to every other vertices in the whole graph with some edge. Okay. So first of all, if we connect each of the vertices over here with edges, then the total number of edges over here will be k choose 2. And similarly, with this n minus k many vertices, that number of edges should be n choose k choose 2. Now there are no edges from this set to this set. So we have to now consider connecting each of these k many vertices with each of these n minus k many vertices. Now if we try to connect these k many vertices with n minus k many vertices, then the total number of edges that is required to connect all these vertices will be k multiplied by n minus k. So therefore, we can say that the total number of edge to make this whole graph complete is k choose 2 plus n minus k choose 2 plus p multiplied by n minus k, which is nothing but the number of edges in Kn, which is this. So basically we have proved this equality over here. Same problem here. We are given a degree sequence of a graph, degree sequence of a graph. So the degree sequence of a graph is the sequence of degrees or the vertices of a graph in non-decreasing order. So if we consider the sequence d1, d2 up to dn, this is called graphic. If there exists a graph with this particular degree sequence. Okay. So consider this 3, 3, 3. So this is also graphic because, oh sorry, 3, 3, 3, 3. So this is a graphic. Why? Because if we consider this graph, then each of the vertices will have degree 3, and the degree sequence should be this. So this sequence 3, 3, 3, 3 is a graphic. Now we have to whether the given sequence this is graphic or not. So the first sequence is given as 5, 4, 3, 2, 1, 0. So there are two ways to prove that this is not graphic. What are the two ways? So first, we can just sum up all the degree values. So if we sum up all the degree values, so that should be 5, 4, 3, 2, 1 plus 0, which is 9, 12, 14, 15, which is odd number. And as we know that the sum of odd degrees in a simple graph should always be even number. So this implies that this degree sequence is not possible. Or we can say that this degree sequence is not graphic. Another way to show is that we have 6 vertices. Since in the degree sequence there are only 6 numbers, so there should be 6 vertices. One particular vertex, consider this vertex over here, this has degree 0. That means it does not have any edges to any of the vertices. But over here, there also exists another vertex which have degree 5. So this should be connected to each and every other one of the vertices. But that will contradict that this vertex over here have degree 0. So using that logic, we can say that the degree sequence is not graphic. So the second degree sequence is given as 6, 5, 4, 3, 2, 1. Again, there are two ways. So first is we sum it up, sum up all the values, and the sum should be 10, 15, 20, 21. So basically 6, 5, 4, 3, 2, 1. This is 21, which is again an odd number. So that means that the degree sequence is not graphic. By the way, if the sum is even then we can say it is possible that the degree sequence is not graphic. Okay, so by checking whether it is odd or even, if this is odd, then we can certainly say that this is not graphic. But if it is even, then it is it may not be graphic, but it is still possible that it is graphic. Okay, so it is inconclusive when we find the sum as even. The second option is, again, we have 6 vertices. 3, 4, 5, 6. We have 6 vertices. One of the vertices has degree 6. Without loss of generality, let's consider this particular vertex has degree 6. But apart from this vertex over here, there are only 5 more vertices. So we can connect this vertex with each and every one of the other vertices. But since this is a simple graph, so there should not be any self-flow, and therefore the maximum degree of this vertex, this can be, in fact, the maximum degree of any vertex, this can be 5. The degree of V can be at most 5. But over here, given that the degree of at least one vertex is 6, so this is not possible. So using that logic, we can say that the degree sequence is not graphic. And there is finally, we have 2, 2, 2, 2, 2. There are 6, 2 here. And finally, we have this. And we cannot prove that this is a, I mean, this degree sequence is definitely graphic. And for that, we just need to give an example of a graph with this particular degree sequence, and that is nothing but a cycle of size 6. And as you can see, that each of the degree of each of the vertex is 2, and there are only 6 vertices. So this is graphic. So now in problem 12, we have to show that if a graph has n many vertices, then no more than n by 2 many edges can be colored with the same in the edge coloring of G. So if possible, let this be not true. So we will prove it by contradiction. So if possible, let there be m edges colored with same color, and not and, where n is greater than n by 2. Okay. So now if this is true, then I mean, coloring of a, I mean, each coloring is supposed to be something like this. So if these are all, if these edges have same color, then none of the edges should be incident. I mean, any pair of, if we consider any pair of edges, then they should not have a common vertex, common incident vertex. So it cannot be like this. This is not possible. We can only have edges like this. So basically, we should have a matching that consists of m many edges. Now, if this is a matching of m many edges, then all the total number of vertices that are involved in this matching, that should be 2m. So 2m many vertices are involved. But according to the, so now 2m is greater than n, because we had taken that n is greater than n over 2. So therefore 2m should be greater than n, but this is the contradiction. Why? Because the total number or the number of vertices is itself n, and it cannot be possible that the edges that we have selected and the vertices that are involved with this, I mean, the vertices that are in the total, all the vertices that are incident to all those edges is greater than the total number of vertices. That is not possible for any graph. So therefore, we can say that our assumption was wrong. That is, it is not possible that we can color more than more than in over too many edges with the same color. So this is we have proved this using contradiction. So over here in the problem 13, we have to prove or disprove that if we are given a simple graph G, that G is equals to if union H, that is if and H are two different graphs, and if we take the union of these two graphs, then the H coloring should be, I mean, the vertex coloring of G should be less than equals to the vertex coloring of H plus the vertex coloring of H. So we will disprove this with an example. So we will take a simple example with 6 vertices. So consider this 6 vertex, key 6. So in key 6, we will have vertices like this, and the edges. So this is key 6. Now in key 6, if we want to color these vertices, then suppose that we just take one color and color this vertex over here. Then none of the vertices, so we have to color this vertex with a different color because this is adjacent to this vertex over here. Now we have to take another color to color this vertex, since this is adjacent to both of these vertices. Then again, we have to take a different color to color this vertex, since this is adjacent to all of these vertices that are colored before. And this is true for every one of these vertices. And therefore, the chromatic number so the chromatic number of P6 is equals to 6. Now, what we will do is that we will take two vertices if and each. Sorry, two different graphs if and each. So first, we will consider if the graph if. So this is our if graph. So this is our graph if. So this is nothing but a bipartite graph. Now we can use only two colors to color this graph. And this is a very valid coloring because there exists no edge from this vertex to this vertex. So definitely this is a valid coloring. And we got another graph over Now we can just use 3 colors to color these 2 graphs. So the chromatic number of F is 2 and the chromatic number of H is 3. So definitely the chromatic number of G is greater than the chromatic number of F plus the chromatic number of H, because this is 6 and F was given as 2 and H was given as 3. So we have given an example where the chromatic number, so this condition is not true. Now finally we have problem 14. So in the problem 14 we have the H chromatic number of Kn is n when n is a positive integer. We have to find the H chromatic number of Kn. So there are two possible values of n. So n can be either even or odd. We consider when n is even. So we'll give an example for only 8 when n is 8. We'll give an example for n is 8, and the construction, the coloring process for any n will be same. So if the n is equal to 8, so what happens is that we first 2, 4, 5, 6. So you consider we first draw the 7 points like this, and take point at the middle. And what we do is that we have to find out each color interest. So we'll instead of 7 points, which is 8 points. Okay, the process are for any. And at the middle, we have one point here. So now, so first what we do is that we take an edge from here to this, and the rest of the, so basically we find a matching like this, and we color this and we color this like color all this just like this. Now again, we can have coloring like this. This is the second. This is the third one. Fourth. And finally, we will have that coloring like this. So using only 5 color, we can color all the edges in K5. But this is not a K5, this is rather K6. And similarly, we can use the similar method to color in many edges. So basically, what we do is that in 5, 6, 7, 4, 5, 6, 7. So if there are 7 many points and 1 point in the middle, then what we do is that first, so this is one map of this n is equal to 7 many points, K7 basically. Oh, this is matching in K8. And once we find a matching, we just color it with this color with one color. Then we find from in the rest of the edges, we find another map like this. This is another completely different matching that does not involve any edge that we have previously chosen. And the third one should be like this. This is the third coloring. This is the fourth one. Fifth one, this. Sixth. Okay, there are the colors. But anyway, so sixth, and this should be the seventh one. Okay, so there are basically 7 colors. One, two, three, four, five. So in case 6, we need in K6 we need 5 colors, and for K8 we need 7 colors. So whenever n is even, sorry, if n is odd, we need n minus 1 colors. But whenever n is even, so when n is even, then basically what we do is that we consider kn plus 1. That is, we again consider this kn, and we consider a dummy vertex over here, and that vertex is connected to each of the vertex in kn. So now this will be kn plus 1, where n plus 1 is odd number, and therefore we can find a valid coloring for this graph. And then after the coloring is done, we can just delete this vertex, and we will have a coloring for kn. And if we use that process, then basically to color this in whenever n is even, to color the graph, we need n colors. So for example, we consider the K4. Then to find coloring for K4, the process is like this. So first of all, we find a matching like this. Then in the rest of the vertex, we find another matching, and we color it with a different color. And finally, this is again a matching, and we color it with a different color. And there are no edges are left that is not colored yet, and therefore this is a valid edge coloring with 3 colors. So whenever n is even, whenever n is even, then we need n minus 1 color. But whenever n is odd, then we need n colors. For example, if we consider K5, so for K5, what we do is that we introduce a dummy variable like this, sorry, dummy vertex like this, and we first color it like this. We find a matching, and then we color it with 1 color. Then we find another matching and color it with a different color. So 3 colors. There are 4 colors, and this can be our 5th color. So we have colored all the vertices, and after the coloring is done, we can just delete the middle vertex and all the edges along with it. So this is a valid coloring for K5 with 3 colors. sorry, with 4 colors. Sorry, there are basically 5 vertices, and the dummy edge was there, so there were 5 colors. Okay, so this is the valid coloring with 5 colors. Okay, so so therefore, if whenever n is even, we can say that we need only n minus 1 colors, and whenever n is odd, we need exactly n colors. Okay, so that's it for this week's session. We will meet tomorrow for week 10. Thank you.